Yes, hello everyone,
Nice.
and welcome to this. I don't know how much edition of this QEI seminar we've done now. So, as a reminder, the Quantum Energies Initiative is this initiative that tries to bring together researchers that care for the resource cost of quantum technologies. Not necessarily to say if it's good or bad, but to really have estimates, and so we don't start developing a technology without knowing if we are allowed to do it by the limitation of current resources. Today, we have the pleasure of welcoming Ilse from Imperial College in London, who will tell us about her work on the impact of quantum coherence on the energetics of quantum information processing. Ilse, thanks for coming, and the floor is yours.
Thank you, Raja, and thank you so much for the invitation. And thank you for being allowed to actually present to you here today what was part of my PhD back in Paris, where we were looking into or studying the impact of quantum coherence on the energetics and performance of quantum information processing. But today I will be focusing on the energetics part of this study. And specifically, I will be discussing this paper that we published a little bit over like 1.5 years ago in PRL, which is called the Experimental Analysis of Energy Transfers between a Quantum Emitter and Light Fields. And this was a great collaboration with, on one hand, experiments, because I'm an experimentalist, and then on the other hand, a great theory group. So before I start my presentation, I would first like to highlight some very important people. So, of course, as I said, this project was done while I was still doing my PhD, which is back in Paris in the C2N lab in the group of Pascal Sinelaar, where we work with quantum light sources. And this project actually got a tremendous help also from Sarah Thomas, who was a postdoc back then, but is now an associate professor at the University of Oxford. And then, of course, we had the wonderful theory team led by Alexia Ofev, who back then was in Grenoble, but of course we all know later on moved to Singapore, with Maria Maffei and Stephen Wine, who actually were tremendous help on the theory side and developed the theory for us to understand what we were actually studying, of course. So as you can see, and as was already introduced in the beginning, actually from the bottom of my slides, you can also see I'm no longer, unfortunately, in Paris. I'm actually at Imperial College in London, where I now work with quantum memories. But let's go back to the energetics part, because that is what my presentation is about. Quantum memories is for a topic for a different presentation at a different time. So I probably don't need to tell you about the importance of studying quantum energetics, but to get us all on board, let me just briefly say this. So often the importance of studying quantum energetics can be explained from a very fundamental point of view, where we have, of course, we are all very much aware of classical thermodynamics, which describes our macroscopic world, where we have many body systems and statistical physics holds. And within this regime, we can define energy flows in terms of useful energy, which we often associate with work, and wasteful energy, which we call heat. However, as we go from the classical regime to the quantum regime, statistical physics breaks down, because we're no longer looking at many body systems, but actually what we have are single particles, single quanta. And these particles are then dominated by fluctuations and randomness. And now the question remains is whether in this domain can we still define such energy flows such as work and heat, and how do the laws of classical thermodynamics actually translate into this regime? Now, to tackle these kind of questions, you can actually take different kind of frameworks. One of them is actually looking at open quantum systems, where you have two particles, A and B, which are coupled together and interact and exchange energy, but they're also coupled to an environment in which they can dissipate their energy. Now, it's an ongoing research endeavor to actually define how to define work and heat, but there's still a lot of work being done on this area. And then the other framework is actually looking into closed quantum systems, where again, we have two particles, particle A and particle B, which are coupled together and interact and exchange energy, but they are otherwise isolated from their environment. So they do not dissipate energy into an environment. Now, such closed quantum system can be described with a Hamiltonian, where we have an interaction term, this VAB, which describes the interaction between these two particles. Now, if initially all the energy is actually in particle A, and it subsequently transfers its energy onto particle B, and we trace out A, we can actually describe the energy flow from A to B. We can divide it into two different kind of energies, which we call unitary energy, which is reversible and can be associated with the quantum notion of work, and correlation energy, which sort of reflects past entanglements between A and B during the process. So these are like two different frameworks you can choose to, well, you can look to study to see whether you can define some kind of quantum versions of the laws of thermodynamics, but this is sort of still ongoing debate. And now, of course, as you are all very much aware, because we're here at the QEI seminar, studying in the quantum energetics also has a very practical importance, of course. So in the last couple of years, we've seen a huge rise in the number of technologies based on quantum physics, with already real-world applications in the fields of quantum computing, quantum sensing, quantum networks, quantum simulations. However, all these kind of technologies need a huge number of resources. This means like lasers, cryostations to keep the temperature down, and anything to actually keep the noise to a minimum. And of course, if you want to do any kind of error correction or fault-tolerant quantum computing, you need a huge number of physical qubits to actually encode your quantum information, which again comes at the cost of a lot of resources. So, however, up until very recently, no one was really actually asking the question, what is the energetic footprint of these kind of quantum technologies? Now, of course, in 2022, Alexia Ofev published this paper in PRX, Quantum, where she called for the need of an quantum energy initiative, where then subsequently we now have this QEI platform, thankfully. But in this paper, it was raised the question whether we can define such a thing as an energetic quantum advantage of these technologies over their classical counterpart. And so is there such a thing, and how do we actually define it or measure it? And in order to answer these kind of questions, we actually have to look at the very fundamental limits of quantum information processing. So what actually, if you break it all down, is the absolute minimum cost of doing minimum energetic cost of doing any of these technologies? So if we look at in the context of quantum technologies, actually it's really interesting to specifically address them as a sort of closed quantum system. Because indeed, what we try with all these kind of quantum technologies is to minimize noise and to absolutely isolate our qubit from the outside. However, measuring the energy transfers in such systems is practically quite difficult. And because indeed it requires accessing energy changes in each system and the correlations and trace back how they were exchanged, and that is quite a challenge. Now, back when we published the paper, so in 2023, there were not that many experimental papers looking into these energetic flows at the quantum level. The papers that were published were very interesting, but they were either addressing energy changes experienced by one open quantum system. So here I show 3 examples where we had polarized photons in a 2-qubit gate, but they were adopting this open quantum system framework, and they were only able to do local energy measurements, so they couldn't trace any correlations, but also these single ions and nuclear spins. Which they used to actually build up a heat engine, and so looking at an open quantum system where all these heat engines could dissipate their heat in some kind of heat bus. Now, the other approach that was taken was actually studying or measuring the average total energy exchange between 2 systems. So really not dividing it between different types of energy, but just looking at the total energy between 2 systems, which was done on platforms with superconducting qubits. Now, we actually took a different approach where we were, instead of these open quantum systems or average energy exchange, we were looking at the unitary and correlation energies in a closed bipartite system, that between a quantum emitter and light fields. And in our study, we actually studied 2 different scenarios, which are pivotal for many optical quantum technologies, such as spontaneous emission and light-light interference. So the rest of my talk will be divided into basically 3 different parts, where in the first part I will be explaining to you and discussing the quantum emitter that we use to actually study the quantum energetics of spontaneous emission and light-light interference. And for that I will also tell you how we actually generate these single photons for quantum technologies. And in the second part, I will start by giving a quick recap of actually the theoretical framework that we use to study the energetic exchanges in spontaneous emission. And for more details, I would actually like to refer back to a previous seminar given by Juliette Moncel, who was the first author on this paper that we used as our theoretical framework. And finally, in the third part, we actually pushed the theory a bit further and studied the energetic exchanges in light-light interference. But first, let's talk about our quantum emitter. So back in our lab in Paris, we actually worked with quantum dot light sources where we have, I'll just get a pointer if that's possible, yes. So where we have a semiconductor quantum dot, which you see over here, which is embedded into 2 layers of gallium arsenide. Now this quantum dot is actually then put inside of a pillar with on the top and bottom Bragg mirrors and in the middle a lambda cavity, which helps to confine the light in a vertical direction such that we can extract light efficiently. Now, this pillar is actually placed on top of this tiny chip that we see over here. And on a single chip, we actually have multiple of these kind of pillars. So multiple light sources. And this chip is then placed inside of a cryostation, which keeps the temperature at 5 Kelvin to actually minimize the noise sources. Now, in order to create indistinguishable photons from such a light source, from such a quantum dot source, we need to keep the timing jitter down of light emission. So a common way to do that is actually using resonant excitation protocols. So we have our quantum dot, which can be described as a 2-level system with a ground and excited state separated by a frequency omega 0. And now if we send in a classical drive with a certain amount of power, which is resonant to this transition, we will excite the quantum dot, thereby generating an electron-hole pair. And if we now wait a certain amount of time, this electron-hole pair will recombine and thereby spontaneously emit a single photon, Fock state. Now, in 2016, it was shown in our group back in Paris that these quantum dot sources are excellent single photon sources with very high brightness, meaning that you can actually generate these single photons at a very high repetition rate, and also great indistinguishability, meaning that consecutively emitted single photons are highly indistinguishable, and also a small G2, by which I mean that every time it emits a wave packet, it will only contain a single photon. However, these quantum dot sources are not just a single photon source. Indeed, if we actually shine our resonant laser light onto our quantum dot with a certain amount of power, and then we increase the power of our excitation laser, we can measure the emission intensity as a function of the laser power, which we call pulse area, which is actually directly related to laser power. And we can see the onset of what we call Rabi oscillations, which show coherent control over the atomic state of our quantum dot. Now, at a pulse area of pi, what we've actually done, we have reached the first maximum in emission intensity. And what we've actually done is that we've created full population inversion inside of our quantum dot, meaning that we've brought the entire quantum dot to the excited state. However, if we park our laser a little bit lower than pi pulse, so anywhere between 0 and 1, what we actually generate inside our quantum dot is an atomic superposition between the ground and excited state with populations PG and PE, and a phase alpha, which is set by the laser. Now, these populations in the energy basis of the quantum dot are directly dictated by the pulse area of our laser, so this theta here, as you can see. Now, if we wait a certain amount of time, once we've generated this atomic superposition, the quantum dot will spontaneously decay, thereby actually emitting a photon number superposition, where we now have a superposition between Fock states 0 and 1, with populations P0 and P1, which are directly coming from the populations initially inside of our quantum dot. Now, it was shown in 2019 in our group that actually the energy coherence that's initially present inside the quantum dot, which is the product of the two populations, or just if you look at it from a density matrix perspective, it corresponds to the off-diagonal terms of the density matrix, that this energy coherence is directly mapped onto a coherence in the photon number basis. So we get the product of P0, P1. And this was actually for the first time in the optical domain shown that this energy coherence directly maps onto this photon number coherence. And this interesting discovery actually opened the path to study the impact of photon number coherence, or as I called it in my title, quantum coherence, on the energetics at the quantum level. So that brings me to my second part of the talk, where we use this, where we actually look at the impact of photon number coherence on the energetic exchanges in spontaneous emission. So as I said, for more details, please go and have a look at the wonderful seminar given by Juliette Moncel, but I will try my best to give a good summary of what they predicted back in this paper in 2020. So here they looked at the impact of photon number coherence on the energetic transfers in spontaneous emission. So the framework here is that we again have two systems, A and B, which I called previously, where A now is a qubit, our two-level system, or our quantum dot, which is coupled to the vacuum of the electromagnetic fields, which we can see as an empty quantum battery, which we call F. Now, if we initially drive our two-level system with a classical field, this classical field will bring will transfer some energy onto this two-level system, which goes as sine squared theta over 2. So with the amount of, depending on the laser power, of course. And we can measure the emission intensity as a function of pulse area. And we can see that we have, again, the onset of Rabi oscillations, showing that we have coherent control over our two-level system. So we can generate any atomic superposition between the ground and excited state. And thus, we also can generate some coherence inside the qubit, which is this small letter S and the product of the two populations, which is just given by cosine theta over 2, sine theta over 2. Now, if then subsequently, after some time, this two-level system spontaneously decays, it will emit a photonic field, which is then whereby the populations in the atomic basis are now mapped onto this Fock state basis. And we actually transfer all the energy that was initially inside our qubit onto the vacuum of the electromagnetic field, so thereby essentially charging the quantum battery. Now, it was shown in the paper by Juliette Moncel and her colleagues that actually this energy transfer upon spontaneous emission can be divided into two types of energy, which in our paper we called unitary energy and correlation energy, but in their paper they called work and heat. And now what they predicted is that actually this unitary energy transfer, so this part of the field, will be directly proportional to the amount of coherence initially inside the qubit. So it goes as h bar omega 0 s squared. Now, they plotted here the predictions according to the theory, where we have the energy as a function of pulse area of the drive, where we can see here in red and green the total energy transfer upon spontaneous emission as a function of pulse area, which only increases. But we can see that the unitary energy transfer actually has a maximum at pi/2, at a pulse area of pi/2. So when we've created an equal superposition between 0 and 1. And this can be understood from the fact that actually indeed at this pulse area, we've actually maximized the product of the two populations. So the interesting thing to note actually is that this unitary energy can be accessed in the emitted field by measuring the increase in the coherent energy. And that correlation energy actually increases fluctuations in the emitted field. But this realization actually allows us to propose a protocol to measure the energetic exchanges during spontaneous emission. Because indeed, what we can actually do by using homodynamic type measurements is access the coherent part contained in the emitted field. So what we do for this is that we use consecutively emitted, spontaneously emitted fields, which we now dub F1 and F2, and we send it into this unbalanced Mach-Zehnder interferometer, where now indeed all these fields are superpositioned between 0 and 1. And so they go into this unbalanced Mach-Zehnder, where one arm contains a delay line, and this delay line allows these two fields to be temporarily overlapped at the final beam splitter. Now, once they've actually entered this interferometer, these fields will pick up a relative phase phi, which is highlighted here in red, which we let freely evolve. And now at the output of the second beam, so here they interfere, and at the output of the second beam splitter, what we actually get is not just our typical noon state, which we would retrieve if the inputs were only a single photon, but actually we get a more complicated output state where we can see that we also get single clicks that are phase dependent, shown here. So if we now place two detectors at the output of this interferometer, N1 and N2, we can actually look at the single counts, which we can see actually go as, well, have a phase dependence, but whose amplitude is directly given by the amount of vacuum population inside our photonic field. So here I show actually two examples of such measurements, where we can see for detector 1 in blue and detector 2 in red. And in the background, you can see these very high or big anti-correlated oscillations as a function of time, where we just let, as I said, let the phase freely evolve. And in the foreground, we see a different measurement where the oscillations or the amplitude of oscillations is a lot smaller, indicating that actually for this measurement, we had a lower P0 component in our field. Now we can access the coherent part of the field by through defining the visibility of interference, which is nothing more than actually the maximum difference between the clicks in detector 1 and the clicks in detector 2. And this we can relate to our energetic transfers, because indeed what we see at the bottom is N1 plus N2, and that's nothing more than the total energy transfer initially transferred from the qubit onto the photonic field. And on top, actually what we have, that we can relate this to the amount of unitary energy transfer transferred during spontaneous emission. So this visibility is directly giving us a fraction of unitary energy over the total energy. Now, using these kind of measurements, we set out to study the energetic exchanges in spontaneous emission. So where we, as I said, have our two systems, our two-level system, which is a quantum dot, which is coupled to the vacuum of the electromagnetic field. And we drive this with a classical drive with a certain amount of pulse area or certain amount of power. And then we let spontaneous decay, thereby emitting this photonic field with variable vacuum population and single photon populations. So initially what we do, we just measure the energy, the emitted energy as a function of pulse area, which we can see here on the right, where we can see that as we increase the pulse area, we get more, we transfer more energy onto the vacuum of the electromagnetic field, which goes as sine squared theta over 2. Now, for several pulse areas, we repeat this process, and we use this photonic field to then interfere it in this unbalanced Mach-Zehnder interferometer, from which we extract the visibility of interference, which is, as I said, directly related to the fraction of unitary energy. So we can see here the visibility of V as a function of pulse area, where all in blue circles, that's the data, and actually in the dashed purple line, that's the ideal case. So we can see that actually our data matches this curve quite well, and that means that actually in our system, that because this tends to go in the very low pulse areas, this goes to almost 100% visibility, meaning that with our system we are very close to the decoherence-free case. In the limit of almost no pulse area, we have only coherence. We have maximum coherence. However, as we increase the pulse area, we can see that our visibility of interference goes down up to the point where at the pulse area of pi, there is no unitary energy anymore. So actually, we don't see any visibility. So using this visibility of interference measurement and the energy balance, we can actually relate this visibility to all the different kind of energy transfers. Because indeed, we can retrieve the unitary energy by multiplying this visibility measurement times the total energy transfer, which is shown here on the top right. And because we're in a closed quantum system, we can then use the difference of the total energy and unitary energy to extract the correlation energy. So we do that, and I plot here again all the energy transfers, where in the black squares we have the total energy transfer, and in the open circles the unitary energy transfer, and the closed circles is the correlation energy, and the lines are just from theory. So now there are a couple of interesting things to note. First of all, we can look at the low power excitation regime, here very close to zero, and what we see here is that we have actually no correlation energy transfer whatsoever, and all the energy transferred upon spontaneous emission is only of unitary energy nature. And this stems from the fact that at very low excitation powers, actually the emission from our quantum dot is solely coming from dipole emission. So there's no entanglement being built up between the qubit and the electromagnetic field. However, as we increase our pulse area, so increase the drive, the power of our classical drive, we increase the energy transfer, but we also see that we increase the correlation energy transfer, which sort of which comes from the fact that when we increase the pulse area, we actually build up population inside our qubit, and as such we also build up entanglement between our electromagnetic field and the qubit, and that gives rise to this correlation energy transfer. To a point actually where at pi pulse we can see that indeed all the energy transfer is of correlation nature. And finally, as was predicted in the paper of Juliette Moncel, we can see that we have maximum unitary energy transfer when the pulse area is at pi over 2. So indeed, when we have initially maximum coherence in the qubit basis, so when this product is maximized. So this was already very exciting for us to actually demonstrate that we were able to do these homodyne type measurements to actually extract the energetic transfers and divide this into a unitary component and correlation energy component. But what we wanted to do next is push this measurement a bit further by introducing pure dephasing to our system. So as I already mentioned previously, is that we kept our two-level system at 5 Kelvin to keep the noise down. However, in order to introduce pure dephasing, what we did next is we actually heated up our cryostation to approximately 20 Kelvin. In such case, this quantum dot will be subject to pure dephasing. However, when we measured the emission intensity of the quantum dot as a function of pulse area, which is shown here for both at 5 Kelvin and 20 Kelvin, we can see that the emission intensity actually didn't change when we heated up the environment of our quantum dot. And this shows that although our quantum dot interacts with the phonon bath, it does not exchange energy with it. And as such, we can still say that we are in a closed quantum system because it doesn't couple to any environment, this quantum dot upon spontaneous emission. And we also know that the electromagnetic field does not couple to any phonon bath. However, because now our quantum dot is subject to pure dephasing, we can no longer write the emitted photonic field as a pure superposition between 0 and 1, but we have to use this density matrix formalism to sort of reflect the fact that we build up correlations between the atom and the environment. And we also have to introduce a new parameter, which we call here C, which actually captures the reduction in number coherence in the presence of pure dephasing. So now our unitary energy is the same as before, but just with this parameter C, which reflects this reduction. And because we're still in a closed quantum system, we can define our correlation energy by doing the energy balance. So we do exactly the same kind of measurements as before. So we do these homodyne type measurements and we extract the visibility of interference, which I show here for both 5 Kelvin and 20 Kelvin, in blue for 5, red for 20 Kelvin. And we can see that where at 5 Kelvin we were very close to the decoherence-free case, now it has significantly reduced. And if we then fit this data to the C cosine squared theta over 2, we can actually extract this parameter. And we can see indeed at 5 Kelvin we are close to 100%. But at 20 Kelvin, we actually are somewhat close to 60%. So really showing the effect of pure dephasing or decoherence on our system. Now using, again, all the energetics shown here on the top right, we translate this visibility measurement into the energetics, where I plot them now all together, and I will walk you through them a bit slowly. But here you can see, again, the energy as a function of pulse area in blue for 5 Kelvin, so what we had previously, with the dashed purple lines, the ideal case, so very close to what we actually measure at 5 Kelvin. But now in red, we can see again the open circles are the unitary energy transfer, and the solid circles is the correlation energy transfer. And we can see that we still have unitary energy transfer, but it's much reduced with respect to the 5 Kelvin case. And this actually immediately is reflected also in an increase in the correlation energy transfer, which sort of shows or reflects that there were entanglements between the quantum dot and environment. So this was the first part of our study. Where we proposed a protocol that allows us to measure the energetic transfers during spontaneous emission. And we could separate, because we're in a closed quantum system, we could define these energetic flows in terms of a unitary component and a correlation energy component, which reflects the build-up entanglement between the qubit and the environment. And so this protocol allows to access past correlations inside during spontaneous emission. Now we implemented this protocol, and this was actually the first experimental study on the energetics in spontaneous emission. And we demonstrated that pure dephasing or decoherence increases the correlation energy as we increase the temperature of the environment. And despite that in both cases, we actually showed that we have maximum unitary energy transfer when initially we have the highest coherence inside the qubit. So that brings me to the final part of my talk, where we pushed the framework even further, and now we wanted to study the energetic exchanges in light-light interference. So in this case, what we want to do is actually, once we've created our photon number superposition state through spontaneous emission, we want to couple this field to another field, which we chose here to be a classical or coherent state. So this is now RB. And what we want to do is that we want to transfer the energy that's initially inside our battery field, we want to transfer it onto this classical field. So how do we implement this? Now, the easy way to do this is actually by interfering our quantum field, which is shown here on the top, with the classical field onto a 50-50 beam splitter, where now we say that one of the output ports of the beam splitter will host our resultant field. So this scenario, so interference at the beam splitter, is actually very important. It's one of the building blocks of actually many optical quantum technologies. As an example, in 2016, it was proposed that using just beam splitters, you can build a universal interferometer, which allows you to implement any unitary transformation. So just as an example, how important such a scenario is. Now, in order to study these energetic transfers in light-light interference, what we do, we actually start by setting the input energies of the field, so the quantum and the classical field, to be equal. So both are sine squared theta over 2, and we let them interfere at the beam splitter. And now after interference, we find that the energy transferred, the total energy transferred from the quantum field to the classical field goes as this cosine sine squared theta over 2 times this parameter, new parameter, CFC, which captures the overall coherence, so both classical and quantum, so both the quantum field and a classical field. And this parameter is upper bounded by the mean wave packet overlap between the classical and quantum field, and is also affected by such a thing as pure dephasing and spectral diffusion of our quantum dot. Now we can, again, if we put two detectors at the output of the beam splitter, we can record the visibility of interference. So if you remember, these are these anti-correlated oscillations in intensities, and we can actually relate this visibility of interference to this new parameter times cosine theta over 2. And as such, what we find is that we can calculate, or we can extract the total energy transfer by actually multiplying this visibility of interference times the initial energy inside our quantum field, so the sine squared theta over 2. Now, because we are, again, in a closed quantum system, we can write down this energy balance, so we can divide this or separate this energy transfer into a unitary component, so how much of the energy going from the quantum field to the classical field is of unitary nature, and into a correlation energy component, where it's actually really important to note that this correlation energy actually can only be a correlation energy stemming from the quantum field. Because indeed, this classical field is a fully coherent field, so it does not contain any correlation energy, and thus, as such, we'll find that the correlation energy transfer from the quantum field to the classical field has to be half that of the correlation energy initially given upon spontaneous emission to the photonic field. And then again, the energy balance then allows us to extract the unitary energy transfer. So we do these visibility measurements. I measure again at both 5 Kelvin and 20 Kelvin and plot here visibility as a function of pulse area, which is shown over here, and where we fit the each of these data curves with this visibility equation over here. And where, as I already said, at 20 Kelvin, this means that we've repeated the measurement, but then in presence of pure dephasing. So we've heated up our quantum dot source before generating this quantum field. And so we fit the data and we extract this parameter, which is at 5 Kelvin is actually 36%, and at 20 Kelvin, 27%. So this sort of shows that we have so that we have this overall coherence between the overall coherence capturing both quantum and classical, but it's again reduced in the presence of pure dephasing. Now, we can then finally plot all the energetic transfers, which is shown over here. Now, all together immediately, so that might be a bit daunting, but I'll go through it. So let us first just look at the total energy transfer. So these are the solid squares or diamonds. We're in blue and in red, where we can immediately see that in both cases we've managed to achieve total energy transfer or energy transfer from the quantum field to the classical field. However, as we introduce pure dephasing, we can see that the total energy transfer has actually been reduced. Now, if we then turn our attention to the correlation energy, this reduction or this decoherence is immediately reflected in an increase in the amount of correlation energy transfer when measured at 20 Kelvin, which you can see here with the dashed black line. And finally, something interesting is actually looking at the unitary energy transfer here in the open circles, where we can actually see that at 5 Kelvin, we only have a positive energy flow for a limited range of pulse areas. So only here in the low pulse areas, which sort of shows that only for this limited range, we transfer unitary energy from the quantum field to the classical field. But as soon as we go somewhat beyond pi over 2, what we have is that actually this classical field is charging our quantum field with some unitary energy. So it's actually the flow in the different way, in the wrong way round, as it were. Now this situation is even worse in the case of 20 Kelvin, where actually we have almost no positive flow of unitary energy, and actually the classical field is constantly feeding this quantum field with unitary energy. Now, the fact that we actually have so little unitary energy transfer or positive unitary energy transfer comes from the fact that we are limited by the mean wave packet overlap between the classical field and the quantum field, and which is also further reduced by spectral diffusion. So our quantum dot actually has some kind of finite wavelength over which it sort of in which it ranges. And furthermore, also the quantum dot transition sometimes, or the quantum dot blinks, meaning not every time that we want to emit a photonic field, it will emit a photonic field. So sometimes we just have nothing on one input of the beam splitter. And this will also immediately impact the visibility of interference. So, but this is all really, really exciting because this was, we were able to do this. We interfere this quantum field with the classical field and extract all the energetic transfers. And now that is actually the end of my presentation, where hopefully I've explained to you how we were able to study the energetic exchange in two very important building blocks of many quantum technologies, spontaneous emission and light-light interference. We were actually able for the first time to directly generate these photon number superpositions from a quantum dot and interfere it with a different kind of field, so a classical field. And for you to these kind of states that we generate are very important for technologies such as quantum key distribution. And so using this framework, we were using a closed quantum system framework, we were able to measure the unitary and correlation energy in spontaneous emission and light interference, and shown that decoherence increases the correlation energy component. But what we hope is that actually that the paper that this serves as sort of a stepping stone to measure so much more energetics at the quantum level, and also understand what actually fundamentally goes on at this level. And then you can think of actually extending this framework to actually look at how do we generate cluster states, or what's the energetic cost of measurement-based quantum computing. And of course, well, the all-encompassing question, is there such a thing as an energetic quantum advantage, or could we harness some of these energetic flows to create some quantum advantage? And with that, I would like to thank you for your attention. And of course, thanks to everyone involved in the project. And thank you very much for giving me the opportunity to present to you today this wonderful project. Thank you.
Wow. I clap by myself. Wow, very nice work. I have quite a few questions, but maybe I will, if anyone has a question, please unmute yourself and go for it, or put it in the chat and I will read it. I give you 5 seconds before I shower Ilse with question.
Maybe I can ask a question. Hi there, Felix Binder from Trinity College Dublin. Thanks, Ilse. for the talk. I'm curious, maybe I missed the exact definitions of the unitary and correlation parts of the energy. Can I think of these being related to the local and global ergotropy of the system?
Ooh, that's a very, very tricky question for me to actually answer because I'm very much the experimentalist in this in this entire project. What I can say, I don't know whether that's going to answer the question, but in all this, because we're looking in this closed quantum system, this is all the while the ergotropy is conserved. So there's no increase in the or maybe I'm saying it wrong, actually, sorry. But I don't.
Sorry.
Hmm?
It sounds like it's all ergotropy because everything is unitary at the global
Yeah.
level, but maybe I
Yes.
missed the part of how you're thinking about this.
I have to ask that I need to ask to Alexia, yeah.
Okay.
Or Juliette, of course.
Nice. Well, I will ask just like a clarification question about this measurement. So you have a measurement that is a homodyne type measurement that allows you to extract the energy of a quantum process. Can I ask you to maybe re-explain a bit how does that work to like, I'm not an experimentalist, of course, but like
Yeah.
how do you get the energy, the fundamental energy out of a physical
Yes. So actually, if you, I'll just do this. So this was actually also shown in this paper from 2019, where they showed that they were able to map the energy coherence, or they showed that the energy coherence initially inside the qubit immediately maps onto a coherence in a photon number basis. And what's the most important part here is that if you look at, so what you're doing here is you're interfering these two superposition states between 0 and 1, and you get this output state, which contains all these different terms. But crucially, actually, what you see if you then look at the single counts actually become a product of P1 times P0.
Okay.
And that can be directly linked to the coherence in the photon number basis.
I see. And from that, you extract the fundamental energy.
Precisely, because you have direct access to the coherence in a photon number basis. You can then link it to all these energetic transfers, or at least the unitary energy transfer.
And this map with the between the energy space and the photon number space, does it also work like for a CV type of state where you have even more photons?
Yes, so what I expect, so we didn't look into that, but like as you go to higher order Fock states, you'll get different kind of coherences, right? So you'll get a coherence, you'll have not only a coherence between 0 and 1, you'll also have a coherence between 1 and 2, or 0 and 2. So there will be different kind of components. What it looks like exactly when you measure it, I don't know, but there will be, you'll have these different kind of coherences, which you can probably also measure, do these kind of measurements to extract information on them.
Yeah, I guess my line of question is a bit going into the how many things can you measure with this technique? It seems like you can measure a lot of things.
Well, at least you can measure, well, up to a single photon Fock state, you can at least measure populations in this basis, and you can measure the coherence inside of this thing. And then from that point on, you can relate a lot of things from there.
That's very interesting.
Hi, Ilse. So I had the same question as Felix, and I think you can measure ergotropy, and so I will get in touch with you because we are working on this local ergotropy and global ergotropy stuff. So if I understood correctly, you're using homodyne detection. But so I wonder is it efficient to measure energy, or at the end of the day, you're basically reconstructing the density matrix of your state and deducing the energy of your state. And I wonder if there is a more convenient way of measuring energy. For example, photodiodes, or I don't know, number resolving measurement, photo number resolving detectors, they measure directly the population. So maybe in that case, you might have, can you say you might have an advantage with respect to the number of samples of the state you need to reconstruct the energy?
So I guess in that case, so when you use PNR instead of these single-click detectors, yeah, you have direct access to the population. But the good thing about, so then you could indeed just send in your photonic field onto these detectors and reconstruct the populations. But what we show by doing this these homodynamic measurements, so interfering these indistinguishable fields at this final beam splitter, that interference all depends, or the single click oscillation really depends on the coherence inside this field. So this type of measurement actually allows us to measure or directly access the coherent component inside this photonic field, whereas with a PNR that would not be the case. So then you do have the population, but you still don't know anything about the coherence part inside the field, if that makes sense.
Yeah, absolutely. Makes totally sense. I wonder also, like, somehow it feels an indirect. So I understand the advantage, and somehow you keep the best of both worlds. So you have coherence, so you can kind of do, say, quantum computation, or at least you can play with quantum mechanics. Whereas if you're just projecting the energy bases, you just get the classical populations. However, imagine I want to use this energy, right? I don't care about just characterizing the state. Now I want to supply power to some machine. Do you think you can do this? Maybe not necessarily, I don't know, maybe even with this scheme. I think it's something we are missing in our field.
No, so I think so. This is definitely more of, as you said, this is really the characterizing of the field. So what we show here is that we are also we can deterministically generate a photon number superposition where we can see from these kind of visibility, okay, what is the vacuum population component, and therefore we also know what is the single photon Fock state component. So once we've characterized that and we know what is the unitary energy inside that field, we can continue generating the photonic fields, but then no longer doing these kind of measurements. But then, for example, as in, well, this will take a while, so I'll scroll like this. But then, for example, you can think of indeed then using this photonic field that you've generated and send it into some kind of gate. I mean, here I interfered with the classical field, but you can also think of maybe, well, you can, if you're doing some kind of C0 gate, I don't know what's going to happen. This is just me going off some kind of tangent, but like you have some kind of energy. Can you harness that energy, that unitary energy, to drive certain gates? Which I don't know precisely, but maybe, or the other option is, can you use this field to actually drive a quantum dot source itself? So actually use that useful energy component and drive the different gates.
Okay. And if my state or my emitter is a complete black box, I don't know where it comes from. I don't know the frequency. I don't know anything. Can you still characterize its energy?
Oh, that will be quite difficult. But I think, well, I don't know in what scenario that will be the case.
No, I'm thinking of, this is a question I've been thinking about for a while, if you can do Bell locality with thermodynamic quantities or something like that. So I really have no idea what you're doing, but I want to certify that I'm doing it well.
Okay.
Good for thoughts, you don't have to answer that.
Yeah, no, but then, for example, well, what you would then want to do, well, without characterization, that will be quite difficult, I would imagine. Because anything that I was about to say would then be, okay, you can interfere the field with itself, but then again, you're looking at the output to then say something about your initial state of light. Yeah, I don't know.
It's okay. Probably you can't. Probably it's impossible. Okay, thanks a lot.
Is there any other question? Or I can ask another one maybe. Okay, so just a last question is maybe a bit more general. So here you have an idea of the fundamental energy consumption, energy cost of what, of emitting a photon, right?
Mm-hmm. Yeah.
Can you then, like, I know and I imagine that the gap with the actual energy consumption, like the power consumption that you need to make this kind of stuff is gigantic.
Yes.
Did you make this kind of comparison? And with this, do you think this can lead to more efficient, like thinking of more efficient way of emitting photon from an energy standpoint?
Mhm.
Or is this just like to have a lower bound?
Well, first of all, yeah, the easiest answer is it is indeed giving you some kind of lower bound. But then this sort of ties also in with the question of one, you can, well, first of all, you can look at these quantities, these energetic transfers, so the unitary correlation energy, and you can optimize protocols based on looking at the energy. So what is the energy you want? Most of the time, that's unitary kind of energy. Can we find a way of maximizing this component, for example? And then the other thing is what I also just said is there then a way to maybe instead of using other kind of resources, can we then use this light, which contains some kind of, which contains this unitary energy components to then drive different gates? So would there be some kind of scenario where we can take this field and then drive, and then put it into some other setup and drive a different gate? Whereas previously what you might have done is just generate a new gate. So again, using laser or generating new fields. So using laser components. So actually, are we able to recycle energy
Yeah.
somehow?
It's interesting.
But yeah, I don't know whether that's possible, but that is in my mind something that would be an interesting thing to look at here.
Yeah. All right. Well, thank you so much.
Well, thank you so much for the opportunity.
I'm stopping this.